In this tutorial we will be looking at how to set up frequency response simulations for passive circuits. We won't be looking at the operation of the circuit in details. For that, please refer to tutorial number 3, which explains how passive networks operate, and in particular it explains in detail the concept of resonance. The first thing that we need to do is double click on project options, then we go to the global units tab, and here we check that the units that we are using are the ones that we want. We can select the frequency to be in kilohertz, for instance. We then can select the capacitance to be in nanofarads, the inductance to be in millihenries, and the resistance is already in ohms, which is what we want. Then click on OK. Next, we have to set up a new circuit schematic. We will start with a CR network. So right click on circuit schematics, open a new schematic, and then we'll call it CR. And now we need to fetch all the components that are required in order to set up the circuit. To fetch the components, press Ctrl L, then we'll type in cap, double click on capacitor and then place it on the schematic like so, press Ctrl L, then type in RES, double click, and then you can right click to rotate it and then left click to place it. Now we connect these two together by simply hovering over like that. We need a ground reference, so we can select a ground reference from up here and place it right there. We then set the values for the capacitor and the resistor to 15 nanofarads and 1.5 kilo ohms respectively. Now what we need is a signal source. This signal source will have to model appropriately the signal source that is provided with the picoscope. And this is a non-ideal voltage source, which is nothing but an ideal voltage source in series with a resistance. So I'll just press Ctrl L again, and then I will fetch an AC voltage source, ACVS, double click on that and then place it. And then I'll also fetch another resistance, so press Ctrl L, type in RES, and then place a resistor like so. Now I want to change the identifier of this resistance so that we make sure that we understand what this is, so I double click on this ID and type in RS. Then I'll connect everything together. The internal resistance of a picoscope signal generator is 600 ohms, so I'll just type in 600 in here. So my input signal will be right here. This is where the input signal meets the circuit. And my output signal will be across the terminals of the resistance R1. I will need to measure both the input voltage on this side of the capacitor and the output voltage right here. Because remember that the picoscope has got a non-ideal voltage source. So the voltage that this source here, V1, produces won't be the same once some voltage has been dropped across this internal source resistance here. So I'm going to use a probe, which is one of these up here. So you just click on measurement probe and you must place it on one of the terminals of an element. You can't place it on the wire somewhere. It has to be on one of the terminals of an element. And then I will rename this V in. Then I'll fetch another probe, and again this has to be right on one of these green squares, on one of the terminals of an element. And then I can simply call this V out. Now I am almost ready to go. There are a couple more things left to do. Firstly, I have to set the magnitude of my voltage source to be 2 volts peak, which would be 4 volts peak to peak. Remember, the magnitude here refers to the peak amplitude, not the peak to peak amplitude. And lastly, what I have to do is determine a range of frequency over which I want to measure my frequency response. To do this, we can go to Project Options again on the left hand side, double click, select the Frequencies tab, and then firstly we select the data entry units, which will be in kilohertz in our case. And we will start at 0.7 kilohertz, which is 700 hertz, and we'll stop at 70 kilohertz. And then in terms of the step, you could have simply a step there and have a linear set of frequencies. But actually, when you do a frequency response, normally you use a logarithmic scale for your x-axis. And hence it makes sense to have a sweep and points that reflect this. To do this, we simply select a logarithmic sweep type there. And then the only thing that we are asked for is how many points per decade we want to use. I will use 20 points per decade. However, when you do your test in the lab, usually 10 points are fine to measure per decade. Then I click on Apply, make sure Replace is selected, and now you've got all your frequencies set here. So click on OK, And now we're all set to go. If you clicked on simulate right now, nothing would happen because this simulator requires you to specify what you want to measure and display. To do this, we simply go on to graphs on the left hand side, right click, create a new graph. This is a rectangular graph, and we will call this CR gain, and then click on create. Now we right click on the graph, go on to add a new measurement. On the measurement type we select non-linear, and then we select voltage, and then on the measurement we select vgain. The data source name is the schematic that we set up, that's CR, so we're fine with that. And now we have to specify, if we're looking at the gain, which one is the input voltage and which one is the output voltage. In order to do this, we simply click on these three dots here, and then we can select this probe as the input voltage, then click on OK. And then we can select this probe as the output voltage, and then click on OK. Now you can see that there's something else that has to be set up, and that's the harmonic index. The simulator allows you to look not only at your main frequency but also at harmonic frequencies, which when the circuits are non-linear is very useful. In your case you don't have to worry about harmonics, you just need to look at your fundamental frequency, and to do that you simply need to set this to 1. So make sure that you set the in harmonic component index to 1 and the out harmonic component index to 1. For this graph, I will just keep the magnitude linear, but we could also have it in dB. Then click on Apply, and then OK. Now simulate. Untick this, keep the window open when finished. Now you can see from this graph that this looks very much like a high-pass filter in that it attenuates low frequencies and amplifies high frequencies. But you can see you can't see it terribly well. So what we need to do, because we used a logarithmic scale for our test, is to change the scale of the graph to a logarithmic scale. So we right-click on that, go on to Options, and then on the Axis tab, simply select log scale for the x-axis. Then go on Apply, and OK. Now you can see that this looks a lot more obvious in terms of the effect that it creates, and that is indeed a high-pass filter. Also, you can now see what I meant by a logarithmic scale and a decade. A decade is basically a difference of a power of 10. So we go from 1 to 10, from 10 to 100, etc. And within each decade, normally in the lab, you only measure where there is a vertical line. So you only measure about 10 points per decade. This is how a frequency response is normally worked out. Now, the next thing that we could do is change the vertical scale to be in dB. And this is also what is usually done. To change the scale to dB, we simply right-click, go on to Modify Measurement, select the measurement we've got, select dB right there, and then OK. Then we have to resimulate. And now we have a graph which has a logarithmic scale on the x-axis and a logarithmic scale on the y-axis as well, because we are using dBs. And this is how you would normally display a frequency response in a technical report. So now we've looked at the gain, so the ratio of the amplitudes of output and input voltage for this particular network. Now let's have a look at the phase relationship between the output and the input voltages. Doing this is really easy. We can duplicate this graph that we've got here by simply clicking on it and then dragging it onto the graph's headings. Alternatively, we can right-click on that and just say duplicate. Now I right-click on the name and select rename, and I'll call this CR face. Now if you double-click on the measurement, all you have to do is, instead of looking at the magnitude of the gain, we are looking at the angle of the gain, and we usually select the angle unwrapped. Make sure that you don't have dB selected here, otherwise things can get a bit messed up. Click on OK, and then simulate. And now you can see the phase difference in degrees between output and input voltage. Notice that the unit of the phase is given right here in the legend when it says deg. Now let's set up one more network, and then the rest of the circuits will be left to you to set up. The next network that we'll be looking at will be an LR circuit, and this will be very, very similar to this one. The only thing that's going to change is that instead of a capacitor, we will have an inductor. So can we duplicate our schematic so that we don't have to make all the effort again? Of course we can. Again, you can simply drag the schematic onto the circuit schematic heading to create a duplicate, or you can right-click on it and simply select duplicate. Then you right-click and you rename it to avoid confusion. We'll rename it LR. And all I have to do now is simply delete the capacitor here by clicking on it and pressing delete. And then I press Ctrl L and I put in here ind, which should get me an inductor. Double click and place it in such a way as to have the probe on one of its terminals. Then connect everything together with the wiring tool. And then you have to change the value of the inductor to 1 millihenry and the value of the resistance R1 to 100 ohms. Now we have to set up the range of frequencies over which we want to do our frequency response. However, if you remember earlier, we went onto project options and selected the frequencies here. This will apply to then every schematic. So if we change the frequency range here, this will change it also for our CR circuit. So how do we circumvent that problem? Well, to have a circuit schematic running with a different set of frequencies other than the global ones, simply right-click on the circuit schematic, LR in this case, and select Options. And then, at the moment, in the Frequency tab, you can see that this schematic is using the project defaults. If you don't want to use the project defaults, simply untick this box. And then you select a new range that you want to use. In this case, for instance, we want to use 500 Hz to 100 kHz. Firstly, change the data entry units to kHz, and then we'll go from 0.5, which is 500 Hz, to 100 kHz. We'll keep the same number of points per decade, we'll also have a logarithmic scale, and then we click on Apply. Then OK. Now, every simulation that I do for this particular circuit, for the LR circuit, will use the new frequency range that I've selected. As before, we have to set up a graph. So we simply right-click on Graph, go on to New Graph, we'll call it LR gain. Again, it's a rectangular graph, and we click on Create. Then right-click, go on to Add a new measurement. You've got everything selected already. You've got voltage, voltage gain. But in this case, you have to change your data source to LR, because that's the schematic where your circuit is. Then you have to check that everything is still correct. So we click on the three dots and we check that the input voltage is in the right place. And then we check again and we look at the output voltage and see that that is in the right place as well. And what we want is the magnitude here. And we can do it directly in dB this time. Then click on Apply and OK. And then simulate. You can see again that we've got a graph that resembles a low-pass filter, but it's not very clear. That's because we have to change the scale on the x-axis to being logarithmic. So we right-click, go on to Options. When we've got the x-axis selected, we select Log Scale, then Apply and OK. I'm going to make this legend a little bit smaller so it's not in the way so much. And now you can see more clearly that we've got a low-pass filter. For the face, we will do again what we did earlier. We right-click on this and we simply duplicate it. And then we right-click and rename it. And then you double-click on that and change the measurement to angle unwrapped. Click on OK and then simulate. I made a mistake on purpose here by not unticking the dB box. So you can see that when you are using dBs to represent an angle, the graph doesn't really make sense. So we need to double click on that again and untick dB and then click on OK and simulate. And now you can see that the angle makes more sense. The last thing that I'm going to look at is how to export data so you can compare it with your experimental data. To do that, I'll just pick one of the graphs at random, simply select the graph that you want and then go on to Graph and Export Trace Data. And then you can simply export your trace data as a text file, and then you can use that in Excel to plot your graphs against the ones that you've measured.